Chapter 3 Digital Circuit. The signal in digital circuit normally we use electrical voltage for logic value. For example, we use low voltage for logic 0 and high voltage for logic 1. Okay, this kind of representation is called positive logic. But sometimes we also use negative logic, which use low voltage for logic 1 and high voltage for logic 0. For high and low voltage level, normally maybe 0 volt for logic low and 5 for logic high. But as you already know that the voltage level for low and high it's not only 0 volt and 5 volt respectively, but there's some length. For example, in CMOS logic, we use 0 to 1.5 volt for logic low or logic 0, and 3.5 to 5 volt for logic high or logic 1. Okay. And for TTL, okay, we use 0 to 0.8 volt for logic 0 and 2 to 5 volt for logic 1. Okay, there's some length. Okay, not only one value of 0 or 5 volt. Okay, to represent the logic function, we can do many ways. For example, we may write some statement, okay, or description, such as the output F is 1 when output Z is 1 only or both X and Y are 1, or the same function but described with different statement. So output F is 0 when input X and Y are different, or all input X, Y, and Z are 0. Or you may write in mathematical expressions as F equals X and Y, or X prime and Y prime and Z. Or you may write with this expression X or Y, or X prime and Y prime and Z prime, and then invert all of this. Or you can write down with a circuit diagram like this, or timing diagram. Or you can use two tables to represent the logic function. Okay, anyway, for the detail we will study for the next chapter, or chapter 4. For this chapter, okay, we will study in detail about CMOS circuit to implement some logic gate. Normally in commercial available IC, we use normally two family of TTL or and CMOS. For example, for TL, we beginning for logic, okay, logic family, normally beginning with 0 and 4. Okay, yes, XX is number, maybe 0001. For example, for CMOS, maybe HC, VHC. Okay, for this, it shows some speed or some power consumption of the IC. Okay. Okay. Before go to the detail, I would like to review some background to understand some basic knowledge about semiconductor. Okay, I change to this. Okay, first, for semiconductor, normally we use silicon. Okay, you know silicon. Silicon is some element. Okay, silicon. Okay, some element that contain 1, 2, 3, 4 valence electron, right? Okay, 4 valence electron. That means in the solid, okay, in silicon crystal, for silicon crystal, after do some bond between another silicon, there are 1, 2, 3, 4. Okay. This 4 is valence electron of this silicon atom, and 5 from this silicon atom, 6 from this silicon atom, 7 from this one, and 8 from this one. Namely, we share electron, okay? Share electron between this atom and this atom, 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 okay? Some kind of this bonding is called covalent bond, okay? Covalent bond. So, and for the electron in the bond, normally this electron cannot move freely to any place in the crystal. That means there is no free carrier in the solid or in the crystal. That means for the normal condition, silicon crystal cannot conduct the current. Anyway, at room temperature, some electron maybe have enough energy to be free from the bonding. Namely, for example, this electron, okay, maybe go away from this region and become free. It's called free electron. Become free electron. That means this electron cannot move to any place in the solid. That means now the silicon crystal can conduct some current. Okay, if there is some electric field or voltage applied to this crystal, okay. And when this electron move out from this area then lack of minus particle, so or minus charge. That means this area by itself will appear some positive charge property. Okay, it's called hole. Okay. This empty space, okay, it's called hole. This hole then have got positive charge, okay, same magnitude as electron, but not negative. Okay. Hole is positive charge. And well, now let's consider if electron move out from this bond and then some hole left at here, right? Okay. One free electron and one hole. If electron at here remove, now there are more one electron and more one hole, right? So you can observe that number of electron and number of hole are the same for the normal pure silicon crystal or intrinsic semiconductor. And let's consider about the hole. Okay, when this electron move, you move to some place, okay, and this region become hole, okay, this empty. can this hole move around in the crystal? Okay, yes, it can. How? For example, this electron maybe move to this empty space and fill this empty area. That means this hole will be disappear. Okay, and this area, okay, then become hole. And maybe this electron also can fill at this empty space or hole, and then this area then become hole. So it's possible to consider that hole at here move to here and then move to here, okay, and so on. So you can consider, okay, hole as one kind of carrier that have positive charge. And now what happens if I dope or replace this some silicon atom with another atom? For example, if I dope boron, or if I dope arsenide, okay, let's consider arsenide first. Arsenide is group 5, right? Group 5 in the element table. That means arsenide have got 5 valence electron. That means if arsenide, for example, replace this position, and 1, 2, 3, 4 of 5 of valence electron of this arsenide atom, okay, will do covalent bond between among the silicon around it. But one left this electron, okay, no bond, okay, to the silicon around it. That means it's possible that this electron, okay, can move, okay, can be free electron. That means this electron, okay, can go to any place in the solid, right? Okay. So now this one is free electron, okay, and this situation, after this electron, okay, go to another place. At here is arsenide, right? At here then lost one negative charge. That means this area then is become negative, okay, become negative. But this negative, it cannot move to any place because it's still do covalent bond, right? Fixed at this position. Okay, the atom that lost some negative charge itself, then it's become positive ion. Okay. Positive ion. By the way, if you note that when you dope with S9 or group 5, there will be one electron, okay, and one ion. Okay. This free electron, okay, that there are free electron, no hole, okay, no hole, okay, from this impurity, okay, or from this S9. Anyway, electron, okay, between silicon atom also possible can remove and then become free electron, and at this empty space then become hole. Anyway, if you count number of electron now, 1, 2, okay, 2 free electron, but only one hole. That means after you dope with S9 or group 5 of element, number of electron is greater than number of hole. This kind of semiconductor is called N-type. Okay? N-type semiconductor. Okay? By the way, if you dope with group 3, for example, boron. Boron is group 3. I mean, boron have 3 valence electrons. When you dope it, then there are 1, 2, 3, right? And it bond with 4 silicon atoms around it. That means there are 1, 2, 3, and 4. Okay, totally 7 valence electrons around this. That means one of this, okay, no, it lack one of it to complete 8 valence electrons around. That means it's possible that electron from here will move and replace at here, fill at here, and now at here then become hole, right? And after electron from the near silicon atom, after move to here, that means this area number of electron become more 1 negative charge. So this boron then become negative ion, okay, or minus ion. By itself, it cannot move, right? Because it's still bonds between 4 silicon atoms, okay, among this one. Okay, so you can note that now, if you dope with group 3 of element, so that there you have excess hole. Okay. So if you count with hole that come from electron go out, become free electron, and at here become hole. So number of hole now greater than number of free electron. This kind of semiconductor is called P-type. Okay? P-type semiconductor. P-type semiconductor have number of hole is greater than number of electron. Okay. For the previous one, N-type semiconductor, number of free electron is greater than number of hole. Okay. So what happens if P-type semiconductor and N-type semiconductor make a junction or contact together at here? What happened? Okay, at this side, okay, dope with S9. Okay, then there are electron, okay, more than hole in this N-type. But for P-type, number of hole, this is hole, okay, number of hole is greater than number of electron. Okay. Okay, now what happened after you connect, okay, or contact between N and P-type semiconductor? Now let's consider number of free electron. The red one, this red dot is electron. Okay, this free electron. Okay, the concentration of free electron in this side is greater than number of free electron in this side. That means the electron from this side, from N side, will diffuse. Okay, some diffusion occur. You diffuse from higher concentration of electron, okay, to the area that have lower concentration of electron. Okay. So what happened if this electron, okay, move to this. That means now this area will move, it lost some negative charge. So now this area then will have only positive charge from positive ion or adenine ion. Okay, this area, okay, we show some positive charge region. Similarly, okay, from this side, hole, okay, hole from this side have higher concentration than this side. That means hole will diffuse from P to N. After hole diffuse, so what happened? This area will have what? Negative charge, right? Of minus ion, okay? Of this minus ion. So now this area, we have positive at this side and negative ion at this side. That means this area there are some what? Electric field, okay, in this direction. So when electron try to diffuse from N to P, it must be in this electric field, and the force from this electric field you try to pull this electron, okay, move to this direction, okay, opposite to the diffuse direction. Okay, similarly, okay, hole from the different concentration between this side and this side, hole try to diffuse to this direction, but when the hole pass through this area, hole is positive charge, right? Then the electric field will push hole to this direction. Okay, so it's prevent. Okay, it's the internal electric field try to prevent the diffusion of electron that try to move from right hand side to left hand side, and to prevent hole from left hand side to right hand side. At the beginning, the intensity of electric field may be not enough to prevent all of diffusion. Anyway, if some electron diffuse, okay, diffuse to this direction, more and more electron or more and more hole diffuse from this region to this region. That means, okay, number of ion, minus ion, and number of plus ion, okay, become more and more. So the electric field, okay, in this region then become stronger, okay, and for and then after that the electric field becomes strong enough to prevent all diffusion of electron and hole. So it's become equilibrium, okay, or steady state. Okay, now there are some built-in electric field, okay, between this region. Okay, it is called this region as space charge layer. Space charge layer, or someone maybe say it as a depletion region. Okay, now what happened if, okay, it is depletion region or space charge region, space charge layer, okay, and this area is N region, okay, neutron N region and neutron P region. And what happened if I apply external voltage with positive at this side and negative at this side. So that means the electric field from this positive and this negative will pass through this direction, right? In this direction, which opposite to this internal or built-in potential or built-in electric field. So if this voltage, okay, is enough, okay, it's great enough to make the cancellation between this electric field, external electric field, and built-in electric field. So, for example, if the electric field is that the strength of this or intensity of the electric field is something like this, and if this side of electric field is this one, so it's cancel together. Okay, and if I increase more voltage, that means in this direction, okay, electric field becomes stronger, and then totally, okay, the resultant electric field now become in this direction. That means hole now, if hole in this direction, it can move to this side, and electron, if in this resultant electric field, then this electron can move to this pre-region. So now electron and hole can flow, right? Can flow freely between this region. So at this situation, okay, the current can flow in the circuit. This kind of applying voltage is called forward bias. Forward bias. Okay, to apply external voltage with positive polarity at P region and negative polarity at L region. So it's become forward bias, and with this forward bias, okay, this element can conduct current. And what happens if I do reverse? Okay, reverse bias. This one positive at N side and negative at P side. So what happened? The electric field due to this external voltage, okay, positive at here, negative at here, okay, the electric field from external voltage source are the same direction with internal or built-in electric field. So the resultant electric field then will be this direction, okay, which prevent the diffusion of electron and hole. So with this biasing, there is no current in the circuit. Okay. So if you want to make this element, okay, can conduct current, you must apply positive voltage at P region and negative voltage at L region, or do forward bias. If you do reverse bias, namely negative at P and positive at N, this element cannot conduct current. Okay, this is the basic. Okay, now back to the lecture note. Okay, now let consider this MOS okay, or MOSFET. It from metal oxide semiconductor FET. FET is from field effect transistor. Field effect transistor. Field is actually field. This is electric field. Okay, electric field. That means the transistor actually is like the resistor that can vary its resistance. So the resistance of transistor can change by electric field control. So actually there are many kinds of transistor, but for this class, okay, we will study just only MOSFET. Okay. For MOSFET, there are three terminals, named gate, drain, and source. Okay, like actually it's like this one, source. Okay, then a source, maybe something like water resource or water tank, and then the water, okay, maybe flow in this pipe, and there's some gate to control amount of water that can flow to drain. Okay, this area, right? This area, okay, can control the flow or the resistance by this gate, okay, to open it or close it. Okay, for this transistor, okay, the structure, basic structure is this one. Namely, there are three terminals: source, gate, and drain. The black one, this is metal. Okay, MOS, MOS, MOS. M is from metal. O is oxide. Oxide in this area is oxide. Oxide is insulator. Okay, little insulator. The current cannot flow through this oxide layer. And S is semiconductor. For example, this one is P. Okay, P type material. Okay, now let's consider if I apply some external voltage source like this. Okay, the question is there some current flow from drain to source or not? Yes or no? Okay, let's consider. Now positive at this side, negative at this side, right? That means this end may be positive or higher voltage potential than what? Than this P, right? So it revert back. That means this junction cannot conduct the current. Anyway, if I add more positive voltage at gate terminal, what happens? If I apply positive at gate terminal, this positive voltage will push hole in this area, okay, away, right, and pull electron, right, pull electron into this direction, okay, push hole, okay, push hole away and pull electron, okay, into this gate. terminal, but electron cannot pass through this insulator, okay, of oxide layer. That means the electron will stop, okay, at here, okay, and this electron also will move to this direction, and then it will stop, okay, or accumulate at this area. If number of electron become greater, okay, become more and more, so now this area, the number of electron become higher than number of hole. So this area then change the property from P to N type semiconductor. That means now this junction and this junction is N and N, right? This junction also N and N. So that means now when you apply the external voltage, okay, the current can flow, right? Can flow from drain, okay, from drain to this N channel. It's called N channel, okay? This path, okay, can conduct current. After you apply positive voltage at gate, okay, the N channel will be generated, and then this transistor can conduct current. This kind of MOSFET is called NMOS. Okay, this N channel right here and N channel. And how about this one? For this one, it's P material at here, P at here, and N at here, right? This one, this also, okay. For the normal situation, even you apply the external voltage at here, like this, the current cannot flow through this junction because one of these will be reverse bias. Anyway, if you apply negative charge at gate, so this negative charge will push electron, right, away and pull hole, right, into this direction. And because this is insulator, okay, the charge cannot flow through this layer. That means the hole will accumulate at this area. And after number of holes become higher enough, this area will have number of holes greater than number of electrons. Then this area then become its property, okay, become like p-type material, okay, of semiconductor, or become p-channel. That means now the current can flow, right? The current can flow in the circuit because P, same p-type material. There is no reverse bias between N and P now. Okay, this kind of transistor is called PMOS. Okay, P is positive. But the conclusion, okay, for NMOS, if you want to make this transistor conduct current, you must apply positive voltage at gate. But for PMOS, okay, to produce this P channel, you must apply negative voltage at gate. Okay, please remember. And now actually you can consider this transistor as switch. Namely, if you do nothing, this and this terminal will be separate together. That means the current cannot flow, right? Cannot flow from this to this. But after you push this switch and contact between this end and this end, so now the current can flow, right? Okay, namely you short, right? You short circuit between this terminal and this terminal. If this switch have 0 ohm or very low resistance, that means when after it short together, okay, this point and this point will have the same potential. Namely, if this point is 5 ohm, this point will be 5 also. Okay, so for this one, okay, if you do nothing, the transistor act as open circuit switch. But if you apply positive charge, it's like you push the switch. Okay, push the switch and make contact between this end and this end. So the voltage of this end and this end then become the same. For this one, after you applied positive voltage at this gate terminal, so it will induce this N channel. Okay, so this N and this N then short together. That means the voltage at this side and this side become the same. Okay, if I assume that this N channel have very low resistance. By the way, for this kind of transistor or PMOS, also if you do nothing, this terminal, drain and source, something like this, drain and source will be separate together. Okay, or there's some open circuit between this. But when you apply negative, it induces, okay, P channel at this area. So now it's like you press this switch, okay, and to make the contact between this drain and the source. So the potential voltage of this point and this point then become the same. Given also this point or drain and source, then because it's short together, so the voltage at this point and this point then become the same. And now let's see some example. If I bring a pair of P and N MOS, okay, to make a circuit, so it is called CMOS, okay, or complement, okay, complement 3 MOS. So it's form complementary MOS. Okay, this one and this one is opposite controlled. Namely, if you want, if you want this transistor Q1 conduct current, you must apply positive voltage at this terminal, right? This one is gate. So after you apply positive, then the N channel, okay, will be generated, and then we short between this and this. And because this terminal connect to ground, this is for ground, okay, ground symbol. Some circuit diagram maybe use this one, some circuit diagram use this one, okay, or some use this one. All of this is ground, okay, ground. Sorry. ground is the reference point that we treat it at 0 volt. Okay, so now this point and this point connect together, okay, directly. How about this one? Apply then this 5, okay, and same. So same potential, the channel P channel not occurred here. That means this transistor act as open circuit. Open circuit. And this one short, right? This one short. So this point and this point then become the same potential. And because this terminal connect to ground, so it's 0 volt at here, right? Then after this transistor turn on, it's like switch, okay, close switch or contact together. So this point then become same voltage at this point. So it then become 0 volt. Okay. So when you apply 5, output becomes 0. If you apply 0, what happened? For this one, 0, also 0, same voltage potential. So the channel will be not induced or generate. That means this transistor still be in open circuit condition. And when apply 0 volt at here and 5 at here, right? That means this gate potential is negatively, okay? It's lower voltage, okay? When compared to with this terminal. So the whole now will be accumulated here and then become P channel. Okay. So now this point and this point then connect directly together. So because this point connect to 5 volt, that means this point then the voltage then become 5 volt also. So when you apply input with 0 volt, your output then will be 5 volt. For the previous one, apply 0, output is 5, and when you apply 5, output then is 0. So it's invert together, right? Input is low, output is high, input high, output will be low. Okay. So this kind of circuit then it acts as inverter. Okay, inverter. Okay, or this one, this inverter. Okay, and for more convenient, because the symbol of this transistor symbol of this transistor NMOS and PMOS, okay, different direction of this arrow. So to make it more easily to remember, so let's change the symbol with this one. For this one of these have no circle, one of these have this circle. Okay, for the circle, actually it is act as negative. Okay, negative control. That means it's if you want this transistor turn on, you must apply 0 volt or logic low at this terminal. Okay, then the P channel, okay, will be produced at here. Okay. Or this switch, if you treat this one as switch, this transistor switch will be turned on when the input voltage at gate terminal is low. So it's called this kind of control that active low. Must apply low logic low to make this transistor active or turn on. Similarly, for this one, if you want this transistor turn on, you must apply positive, right? Must apply positive voltage. Then internal will be generated. That means this point and this point short together. So this point is 5, then this point then become, this point is 0, okay, 0 volt or ground. This point then become 0 volt also. Okay, so for this one will be turned on when you apply logic high, right? Then it's called active high, okay. Active high element. So please remember, okay, this is the basic one. Okay, active low and active high. Okay, so you must remember this basic circuit of inverter. And please remember the symbol for active high and active low. For active low, they will circle, or sometimes I will call inversion bubble. Inversion bubble. Okay, bubble. Okay, to name it is show the negative, right? Negative meaning. Okay, if active high, there is no inversion bubble, but for active low, we have inversion bubble. Okay, so from now you just consider that this gate, okay, gate terminal that used to control this transistor as switch. If this one is active high, you must apply high of 5 volt at this gate terminal, okay, to make the channel, okay, link or short between source and drain. Okay, after this point and this point, okay, short together by turn on this transistor with positive voltage. So this point and this point then become the same voltage potential or 0 volt. Okay, for this example, if you want this one to turn on, you must apply 0 volt or low, okay, to make this transistor turn on or generate this P channel. That's all. Okay, just remember. Okay, the control again the control signal, okay, we apply at gate, okay, the gate terminal to make the connection between drain and source. Okay, if the channel connection channel generate, then the voltage at drain and source terminal will be the same. Okay, another example. Assume that you can remember. Okay, before that, please take a note. Okay, for inverter, actually another kind of CMOS circuit, you must connect PMOS at the upper part of the circuit that connect to positive voltage of VDD. But for NMOS, must use at the low part of the circuit that connect to ground. Okay, you cannot swap between P and N. Okay, why? For example, for this one, NMOS at here, right? When you apply 5 volt, then the 5 volt will induce N channel at here, right? N channel at here. Okay. We call 5 at here and 0 at here. 5 is higher, right? 5 volt is higher than this side, so it can induce some N channel. Okay, but if you switch. Okay, you change between this and this, namely NMOS at the upper part of the circuit and PMOS, okay, connect to the lower part of the circuit. Now, if I apply 5 volt, what happened? It is 5 at here and 0 at here. Namely, the gate terminal now have higher potential than this side. So what happened? Then you will attract or pull, okay, electron accumulate at this area, right? But after you apply 5 volt, right? Feed in 5 volt at here. So this area still be N-type material. So there is still some reverse bias junction between N and P material. So this one cannot conduct. Okay, so it's to be off condition. And how about this one? When you apply 5 at here, and this side also 5, okay, same potential, so this transistor cannot turn on. That means now this one not turn on, this one not turn on, so you cannot use, right? Or if you apply 0 volt, 0, 0 at the same, so this one not turn on, and because of this is NMOS, and you apply 0 at here, right? 0 volt at here, okay, 0 volt at here, and but 5 at here, so the hole will be accumulate at this area, right? For a hole, okay, hole with positive charge, okay. So this is p-type, okay, so to be p-type material, okay, at this area, right? For a lot of hole. Again, this junction or this junction, okay, junction between N and P or P and N, one of these must be biased reversely. So this transistor cannot conduct the current, so you cannot use. By the conclusion, you must use CMOS with this configuration, okay, NMOS at the lower part of the circuit that connect to ground, and PMOS, okay, or active low element, okay, connect to VDD or positive voltage. Okay, now let's consider this kind of circuit. For this one, there are 4, right? 4 transistors. 2 of them are active high, okay, no inversion bubble, and these 2 transistors is active low. So let's analyze this one. Okay, now if I want to analyze the function of this circuit, what should I do? Okay, A and B, 2 bits, right? So it just apply 4 possible values. For example, let me apply 0, 0 at here, right? Or low, low at here. Okay. Okay, now let's consider which transistor turn on, which one is turned off. Okay, which one turns on, which one turns off. Okay, this one. How about this one? It's active low, right? There is some inversion bubble circle at here, right? So when you apply low, so this transistor will be turned on. That means it will short between this point and this point. And terminal B, input B, if applied with logic low, this one low, right? So this one turn on. Okay, it will short between this point and this point. How about this one? This one is active high, right? But you apply 0, so this one is off. How about this? This one active high, but you apply low, so it cannot conduct. That means now the output Z, okay, connect to positive VDD, okay, via this path. That means now the output Z then become high, okay, or 5 volt. So when you apply 0 volt, or logic low, the output then become high. And if I apply 0 and here, 1 and here, what happened? This one active low then turn on, but this one turn off, right? This one turn off, and 1 and here, right? Active high, then this one turn on. So now the output disconnect, right? Disconnect to VDD, but connect to ground via this path. So now output become 0 volt or logic low. Okay. And if I apply 1 at here, 0 at here, okay, and this one active low, then this one is turned off, and this one turn off. How about this? Low, or this one on, high, right? Active high, and 1 or high at here. So this one on, and how about this? This one 0, right? So this one active high, but you apply 0 at gate terminal, then this transistor is off. So now the output Z, okay, have this path, okay, connect to ground, then output Z become 0 and 1 1. This one turn off because of active low, right? But you apply high at here. This one also active low, but apply high, so transistor Q4 is off, and high at here, right? High at here and high at here. So this one turn on and this one turn on. So there are two paths, right, that connect output Z to ground. So now output Z then become 0. Okay, this table just show all 4 cases of input AB, okay, to make the output Z, okay, on or off, high or low. Okay, from this circuit, the transistor Z will be high, just only the case of A and B is low both. So the function of this circuit is actually NOR gate, NOR function. Okay, this one. Okay, how about this one? For this circuit, let's analyze. Again, actually you can consider a number of input, right? Input signal. There are 2, right? 2 bits. So there are 4, right? 4 possibility: 0 0, 0 1, 1 0, and 1 1, right? When you apply, for example, when you apply 0 0, 0 at here, 0 at here, right? This one turn on, this one turn on, right? Active low, this active high will off, active will off. So the output Z connect to VDD, or output Z then now become high, right? Okay, output Z then become logic high or 1. Okay, and if I apply what? If I apply 0 1, 0 at here, 1 at here, this one turn on, right? Okay, because of active low at here, and 1 at here, this one turn off. This one active high, but apply low, so this one off. This one on. So for this example, the output Z now connect to what? VDD, then it become high. So this one also output is high. For 1 0, I think will be the same. For 1 1, for 1 1, okay, 1 at here and 1 at here. This one on, this one on. Now the output connect to ground, then output then becomes 0. Okay, by the result, when you apply input A, B, and output Z, right? When A, B 0, 0, this one on, there's some part that connect to VDD. Okay, so the output then become high. For 0, 1 or 1, 0, okay, one of this on, but one of this off. So when you consider this one, you see that this one turn on, right? So output then become high. Or 1, 0, 1, 0, 0, right? A is 1, B 0. That means this is 0, right? Then this one turn on. So output C connect to VDD, then become high. And when apply 1, 1, this one turn on, this one turn on. Okay, turn on both, and then connect to ground. Then output become 0 for the input 1, 1. Okay. And after that, you just consider again what kind of function of this circuit. Okay. So for this one, it's NAND gate. Okay. How about this? For this, oh, there are what? How many? 1, 2, 3 input, right? Then you must analyze by applying the input A, B, C with the value of low, 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 high, until high, high. Okay, 8 case. For example, if you apply 0, 0, 0 at here, this one active high, right? But you apply 0, then it's off, off, off. And this one on, because active low, and active low. And you apply 0, 0, right? Logic low. Then this transistor will be on. So the output then connect to VDD, okay, with some of this part, right? Then it become high. Okay, and you do something like this. Then you will get the complete truth table, and then you will know that, oh, this one is NAND, okay, 3 input NAND gate. Okay, will be low just only when all of the input is high, right? When all of the input become logic high, then we make this one on. So the output will be connected to ground. Okay, if I want to do more input, so I just add, right, number of transistor, okay, into the circuit like this. By the way, we cannot add, okay, this transistor into the circuit as we want to add. Why? Because let's consider when this transistor turn on. For example, I apply 1, 1, 1. Okay, this transistor turn on. Okay, some channel. Okay, N channel will be generated, right? At here, for the ideal transistor, this channel will have 0 ohm resistance. This one also 0 ohm, all of this 0 ohm. So the output then connect to ground directly with this 0 ohm path. That means output is 0 now. But what happened, okay, in practical, if this have some internal resistance? For example, when this transistor turn on, resistance assume it's around 10 ohm. Okay, for example, of this 10 ohm, and if the current flow to its transistor is for example 20 milliamp, for example, that means when apply 1 at here. Okay, this one turn on, this one turn on. So because of 10 ohm, right? That means the voltage across this one is what? 200, right? Or 0.24. Okay, this one also 0.24, 0.24. Okay, if all of these have same resistance when it's turned on. Okay, when it's on. Okay, now if I add transistor, for example, add with 10, that means the voltage drop of this 10 transistor, then it's become what? 0.2, 0.2, 0.2 for 10 transistor. That means the voltage now is become 2 volt, right? Voltage across all of this. That means this point is 0 volt or ground, but it's plus minus, right? 2 volt. That means this point have higher voltage than the point with 2 volt. So now output then become 2 volt also. But 2 volt is not logic low, right? Okay. So some error occur. That means you cannot do the design by add number of transistor as many as you want. Okay, the limitation okay, is called the limitation of number of input. Okay, it's called fan in. Okay, fan in. Okay, fan is like its shape, right? Like fan. In is input. Okay, for example, something like this. Okay, 1 2 3 4 5 6 7 8, right? If you design this one, maybe your output may be lost the logic level. So how to solve this one? You may, for example, to separate two sets of input 4 and 4. 4 of this, right? So now you can reduce number of input, and then you just combine this output together. Okay. Okay. Now you know the fan in. Okay. Okay. Another example of logic gate. Okay. For this one, if you can remember, this part is inverter, this part is inverter also. So it invert out invert, then it become buffer. Okay. That means if you apply 0 at here, output will be 0 also. If you apply 1 or 6 high at here, output will be high. Okay. Okay, or you can analyze if you cannot remember. Okay, you can analyze directly. For example, when you apply 0 at here, active low, right? So turn on Q2 and Q1 turn off because it's active high. So now this point then connect to VDD 5 volt, that is 5 volt at here, and this one active low, but this one active high, this one off, this one on. Okay, when it's on, you short between this terminal and this terminal. So this terminal and this terminal then have the same voltage, namely output now then become 0 volt. Okay, but it's connected to ground. Okay, when apply 0, output also 0. So this is buffer. You can analyze, you can do analyze, okay, directly. But if you can remember the pattern, okay, it will make you do faster. Okay, do analysis faster. If you remember the pattern of inverter, input, output. This one connect to ground, okay, for active high element, and active low element connect to VDD. Okay. And how about this one? For this one, if you can remember, this part is NAND function, right? NAND function to input NAND. And this part is inverter. Okay. So then invert of NAND, then it become AND gate. In practical, AND gate is invert of NAND. So by itself is will take time, okay, have longer delay time. Okay, AND gate, okay, you have AND gate has got longer propagation delay time than NAND gate. Okay. So if you can remember the pattern of the CMOS for inverter or something like that, okay, you can do the circuit analysis easy. Okay, so please remember, it's pretty easy, right? For example, for inverter, right? One of these will connect to VDD, and this one connect to ground, and this one connect to control signal, right? And the output is from here. Okay, for example. Okay, that's all for today.